Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face Trending List, published on July 1st, 2025, just a couple of days ago. It finds that, surprisingly, most models that get really good at math actually fail to transfer those new skills to other areas. The paper is titled, "Does Math Reasoning Improve General LLM Capabilities? Understanding Transferability of LLM Reasoning," and the implications for how we train these models are pretty significant. The authors dig into why this happens, comparing different training methods on a QN3 model. Also, the authors shared their work on GitHub, and it's a really complete package. You'll find all the code, their full evaluation framework, and the analysis tools from the study. They even provide links to their pre-trained models, so you can replicate their findings or experiment with them yourself. Alright, so to really test this, the authors compare two popular training methods. The first is supervised fine-tuning, where the model learns by studying examples of correct reasoning. The second is reinforcement learning, where it learns by getting rewards for right answers. This first figure shows the results on a QN314B model. For math tasks, both methods improve performance, but reinforcement learning does better. For other reasoning, it transfers its skills much more effectively. But the real story is on the right. For non-reasoning tasks, supervised fine-tuning causes catastrophic forgetting, with performance plummeting. In contrast, the reinforcement learning model actually improves. Building on that initial finding, these next two charts broaden the comparison across more than 20 different models. The authors introduce a metric called the Transferability Index, which measures how well math skills transfer to other domains. A positive score means good transfer, while a negative score shows performance actually got worse. In the top chart, for other reasoning tasks like science or coding, you see a clear split. The orange dots, the reinforcement learning models, are almost all positive. The blue dots, the supervised fine-tuning models, show poor transfer. And the bottom chart is even more stark. For general non-reasoning tasks, supervised fine-tuning consistently degrades performance, backing up that idea of catastrophic forgetting. This table then details the specific performance numbers behind those charts, really laying out the evidence. It compares the base QN314B model against different fine-tuned versions. Now, one supervised fine-tuning model was trained using what's called chain of thought, which means it learned from examples that showed the step-by-step reasoning. But even with that, looking at the non-reasoning section, the supervised fine-tuning models absolutely crater, dropping from a baseline average of 45.7 to as low as 21.1. Meanwhile, the reinforcement learning model improves to 53.2, directly showing how it avoids catastrophic forgetting. So to visualize what's happening internally, these charts use a technique called Principal Component Analysis, or PCA. It's a way to map out how the model understands different tasks. The blue dots are the base model before training, and the orange triangles are the model after. The distance between them shows how much its internal representations have shifted. You can see in the top two rows, for the supervised fine-tuning models, that shift is huge, especially for non-reasoning. But the bottom row, for reinforcement learning, shows a much smaller shift, suggesting its core knowledge remains far more stable. So putting it all together, the core message is that how you teach an LLM math matters immensely. Supervised fine-tuning often leads to catastrophic forgetting, destroying the model's other skills. But reinforcement learning successfully teaches reasoning while preserving general knowledge. The analysis suggests this happens because reinforcement learning makes precise, targeted updates, while supervised fine-tuning causes a much broader, more disruptive internal shift. It's a critical insight for anyone building these powerful models. That's all for this week's AI Research Roundup. Thanks for tuning in.